I thank Rohini and the Academy for giving me this opportunity to talk about some aspects of Professor Sudarshan's work. I belong to a generation where we all grew up looking up to Sudarshan even before we had met him. I met him first in 1976 when he had come to American College to visit Manuel Tangaraj, who was the principal at that time. Then he arranged for us to have a meeting, and at the end of the meeting, Professor Sudarshan was kind enough to invite me to join him in Austin. That's something which I never made. Subsequently, now, but what is more relevant is I come from an institute which was reconstructed and reconfigured by him, and his presence is always awe-inspiring, but in some sense he is very easygoing also. I remember those days when he was in Math Science IMSc. I did not have a car, but I was afraid, but he had no fear of hanging on to me on the as the pillion rider on my bullet. Another instance I should definitely quote to indicate how he can make people feel kind of at ease with him. Once I had just come from US, there was a carton of cigarettes on his table. So when I went in, I said, "Thank you very much." He said, "No, this is not for you. This is for someone who can ask me a question which I cannot answer." Now, this was the true, real intellectual arrogance which defined him. I can keep saying many things, but one thing that has kind of lived with me as an injury is that in one of the meetings, probably somewhere in Bangalore, I don't know if Professor Mukunda was there, we were walking, he tripped and well, I tried to help him. I could not hold completely, I just put out my arm. But so he fell slowly, but I couldn't stop. Then even before he got up, "Oh, you have broken your hand." Because I had just a little earlier, I had this metal plate. So he was so confident that I would not have allowed that to happen if I did not have that broken hand. Anyway, Sudarshan's interest in optics dates back to his days in Madras Christian College where he was a student. He has several times told me that Dr. Tangaraj's teaching of Jenkins and White was a very big influence in him. When he joined Math Science, or when he took over Math Science as director, before I joined, the first time when we meet, he had a very earnest request to make of me. He said, "Simon, you should somehow find Dr. Tangaraj and get me a portrait of him." People who have, and I did find a very good portrait. People who have visited IMSc during that period will remember that it used to decorate his office as long as he was there. Now, so classical theory of optical coherence was developed by Emil Wolf for free fields using sequencer expressions like this, where angle bracket stands for ensemble average, and plus denotes the positive frequency part of the real signal, which means it will be single side spectrum. Real signals will have spectrum on both the positive and negative side, but this will be single side spectrum, and the minus denotes the negative frequency part. The positive frequency part is called the analytic signal, and this has been in vogue in optics from the days of Dennis Gaber. Now, Mandel, who was who had not yet joined Rochester, developed a theory by which he connected these coherence functions to correlations between photon-electron counts. Okay, so with this combination, even Hanbury-Brown twist effect, they were able to explain, which was to begin with thought of to be a purely quantum effect, but it turned out to be largely a classical effect. Now, it is at this stage, subsequently, in 64, Mandel moved to Rochester. By that time, Sudarshan had moved out of Rochester to Syracuse. Now, 63, Sudarshan has several times told me that one of his greatest contributions to optics is his role in bringing Mandel to Rochester. Now, 63 is very special for optics because two high-energy physicists enter this domain. One is Roy Glauber, who was at Harvard, and the other one is Sudarshan. And these are the four papers belonging to that year. Three of them by Glauber. The first one is Glauber. You can see it is submitted 27th December and appears 1st February. And Glauber again writes a long paper in Physical Review that is submitted 11th February and appears in June. Then Sudarshan writes a paper which is submitted 1st March and appears in 1st April. Now, this is a kind of things seem to have been communication seems to have been fast in those days, because recently there is this quantum supremacy paper that I found that it has taken 2 days plus 3 months. Such a paper which has made so much of hype. Many people say it is so-called quantum supremacy, but in any case, things have moved very fast in those days. Now, then Glauber followed up with a very long paper. Now, normally in this kind of a situation, when we are talking about Sudarshan, you don't have to talk about anybody else, but it's virtually near impossible to talk about Sudarshan's work on optics without talking about Glauber. Because for one thing, he got Nobel Prize for that work, and also the kind of polemics Glauber brought into this field from the day Sudarshan published his paper, even including his Nobel lecture, there is polemic. If I had a long time, I would have loved to go over these things in more detail, but I will just move on. Now, the quantum theory of optical coherence involves coherent states in an essential way. And this usefulness was first pointed out by Glauber, so we should give the man the credit. Coherent state is a combination of all Fock states with these kind of coefficients. Now, since these are eigenstates of the annihilation operator, which is the positive frequency part of the field, if a state is a convex sum of coherent states, then any anti-normally ordered operator, its expectation, this is the most general anti-normally ordered operator, its expectation value, quantum mechanical expectation value, can be simply calculated. It comes from this eigenfunction property. So, this is exact quantum mechanical expectation, but it will look like the average in a classical phase space. Now, this is the fundamental manner in which phase space functions play an important role in description of quantum optics. This is, I want to read this portion by Sudarshan. Statistical states of a quantized field have been considered recently, and that's Glauber's work, and a quantum mechanical definition of coherence function of arbitrary order presented. This is also Glauber's work. Then Sudarshan states his important result. It is the aim of this note to elaborate on this definition and to demonstrate its complete equivalence to classical description as long as no nonlinear effects are considered. Now, this may, for a moment I thought this is probably overstated. Then there is a conference proceedings from April, 1 month later. There also he repeats the essentially this same position. Now, if you look carefully, this is a paper by Wolf. This is the paper which precedes Sudarshan's paper. This path-breaking paper of Sudarshan is preceded by Wolf and Wolf and Mandel. And they say that since this paper was written, Sudarshan has demonstrated that the semi-classical and the quantum mechanical descriptions are completely equivalent at a formal level, as long as, again, no nonlinear effects are considered. So, Sudarshan's main work was to establish that quantum optics can be treated exactly on the same format in which we treat classical optics. Okay, so again, this is so he proved that every density operator of a radiation field can be written as a convex sum of coherent states. And this he proved by giving an inversion formula. He reconstructed phi offset in terms of rho. In fact, that's the only way you can prove such a statement. Now, he also notices that hermeticity of rho implies reality of this diagonal weight function. And the requirement that trace of the density operator has to evaluate to unity translates into this condition that the integral of phi has to be unity. Now, these two conditions will reality, and this will make it phi offset into a probability or a genuine weight function if phi offset was also real. And that's both a necessary and sufficient condition. But it turns out that the positivity of rho does not translate to point-wise positivity of phi. The condition positivity of rho places on phi is a much weaker positivity condition. Several integrals have to be positive. Now, for instance, there are two simple cases I have pointed. If phi offset can be very singular in some cases, a typical case being that for the nth Fock state, phi offset will be the 2nth derivative of the delta function, which is delta function we may not take it as singular, but derivative of delta function is definitely singular. Then there are some states for which phi offset can be, the Fourier transform of phi offset can be a growing Gaussian. Gaussian with the wrong signature, which is really so if you allow this kind of a singularity, then phi offset always exists for every state. That is the general content of Sudarshan's main result. But that the phi of z is singular or negative does not affect anything, because phi of z always occurs under an integral as a kernel. Therefore, only its smoothen values contribute to. Now, so therefore, I think here is a first. This is the first time a quasi probability is introduced into optics. Okay, I make this underline this statement because a similar statement, statement about this is made in the announcement of the Nobel Prize that Glauber introduced quasi probability. Now, here is comes something important. If the phi of z of a state of radiation is a genuine probability, then that state doesn't have anything to offer beyond classical optics. Okay, because we can understand it as a classical sum of classical states, or a true probabilistic sum of classical states. So only in cases where phi of z fails to be a genuine probability distribution, the state will have aspects which are beyond the grasp of classical optics. Okay, so these are the useful ones. These are really the useful states from a technological point of view. Now, also I want to underline here that non-classical, so we will call these states non-classical states for which the phi of z is not a genuine probability but a generalized probability. We will call it them non-classical. But non-classical states are hard to come by. Okay, in spite of all these polemics that was going on in '63, neither Glauber or anybody found any particular non-classical state even for 10 years. That had to wait for Mendel. A laser beam, quantum optics was developed mainly to consider laser beam, but it turns out that the laser beam is the most classical light beam one can have. To emphasize the importance of non-classical states of light, see, here is a beam splitter. Sometimes we draw beam splitter diagram like this. One beam goes from the left and it gets split into two beams. This is a wrong diagram. I mean, even when there is no intensity here, there is a beam going, it's in vacuum state. These are what we call beams, they are modes. So this is the correct diagram. Now here is a statement. So actually it's a misnomer. Beam splitter should have been called a beam mixer. That's what it does. Anyway, so a beam splitter has two input ports and two output ports. Into one input port you send either vacuum or another classical wave like a coherent state. Into the other one you send some light. Now the output two modes will be entangled if and only if this state is non-classical. So no non-classicality means no entanglement. Okay. Now today quantum technology seems to be the key thing, and whatever form it takes, 50% of it is going to be optical. I think 50% of the technology will come from particle aspects, 50% will come from quantum aspect. So the 50% of that quantum technology has to be governed by non-classical state, and these non-classical states were first formulated by Sudarshan. That is this major contribution arising from the. In fact, Sudarshan's diagonal weight function allows you to say whether a state is classical or not, but it does not immediately give you a measure of non-classicality. So this, whereas measure of entanglement exists. So therefore this situation, it has been suggested that this situation can be turned around to define a measure of non-classicality. So you put the non-classical light into one port of a beam splitter, the other port you hold at either a coherent state or vacuum, then look at the output quantum of entanglement that you can attribute to the non-classicality of rho. ECG has written maybe several dozens of papers in optics, but I thought I will concentrate only on this. Maybe I should, this is, see, originally some people may think that when Sudarshan wrote, saying, give unto Glauber only what is his, it is not an expression of disappointment, because 85 he said he has learned to live with disappointment and lack of recognition. But here, what time, and if I had time to read all these underlined things in the document that was put out on behalf of the Nobel Committee called the Advanced Information, many of these things stated, are clearly wrong. They have taken simply what Sudarshan had contributed and have attributed to Glauber to justify the Nobel Prize. It is that part. So his statement that should be read in two parts. He clearly says, give unto Glauber what is his. But don't give unto Glauber what is not his. I mean, give unto Glauber only what is his. That's what. But I don't want to take more time, and thank you very much.